Welcome to Pre-Calculus. Today we will investigate investment, specifically looking at compound investment. And we want to calculate initial or final amounts. We'll take a look at two examples. Our first example is about Sarah Wong investing $4,537 in a retirement account with a fixed annual interest rate of 4.55% compounded quarterly. What we want to solve is what the balance will be after 17 years. So we've got to think about the situation. This individual is investing a lump sum, $4,537 in a retirement account, and is earning interest on that initial investment. We will assume that there's no additional deposits. It's just the single deposit of $4,537. The interest in such a situation can be compounded, or in other words, calculated for that lump sum different ways. And really the different ways have to do with how frequently over the year that initial sum is used to calculate the interest that's gained. And we have different words that clue us into how frequently that's occurring during a single year. So this one involves a quarterly investment, which means that 4 times in the year that interest will be calculated. And again, we're interested in after 17 years of this kind of recurring interest calculation, how much will be in the account. So we are expecting something greater than 4,537. Sarah Wong will want to see some kind of growth with her investment. So what we really need is some type of formula. And what we've got is really an exponential function for compound interest. So let's give that formula. The compound interest formula goes like this. So the future amount, really the answer we're looking for here, we're going to call A, and it's a function of time. So A of t equals the initial amount. So we're going to call that P for principal. And we've got to multiply that times the base. So the base, because it's a growth function, it's going to be 1 plus some kind of decimal value. And the way we'll get that, it's the rate divided by the number of times that we invest over the year. So for us, that's about this quarterly. And then because it's exponential, it's raised to the power of that same n value times time. So I've got principal labeled here. That A of t is the future amount. Principal is a fancy way of saying that's how much we started with. That's the start investment. And then again, R describes the interest rate. And we got to note that that is going to be as a decimal. So a lot of times interest rates are given as a percentage. In the formula, we want to convert it to a decimal. And then the n value is the number of times interest is compounded in 1 year. And then, of course, t is our time. And you can guess the unit for the time is going to be years. So for this question, we kind of, at this point, know what we're looking for. We're looking for A of t. And so what we need to do is plug in values for the principal, the rate, the n value, and the time. So we'll just start setting it up. I am looking for A of t. My principal is the initial investment. So that's going to be the $4,537. That's times the base 1 plus, so it's a fraction of my rate divided by my number of times that I compound the interest in 1 year. So if the rate is 4.55%, that's equivalent, if I move the decimal 2 to the left, to 0.0455. And that's the decimal value that I want to use. So that rate, you do want to convert it over into a decimal over the n value. So we've already said our compounding is quarterly. So that makes me kind of make a leap to say that the n value is 4. And again, that's because I would calculate the interest 4 times in the year. And I use that value again in the exponent. So it's to the power of nt. So it's to the power of 4 times the number of years I'm interested in, and that's 17 years. And so really at that point, once we've got it set up, all I need to do is take that expression and use a calculator to evaluate. So let's head over to Desmos, and we'll round this one to the nearest thousandth, but let's get to the calculator first. And we'll enter that expression as we wrote it. So again, 4,537 times 1 plus the fraction 0.0455 over 4. And we are raising that to the power of 4 times 17. Make sure I stay in the power. You got to put parentheses there. And that gives us quite a bit of growth. Over 17 years, if Sarah Wong did not make any additional deposits in the account, the value would nearly have doubled. It's $9,790, and we'll just round to the nearest hundred since that would give us the cent, 38 cents. So a good investment over a long period of time. And that really is what's making the difference here for this situation. So A of 17 really has the approximate value of $9,790.38. So in this example, we had information that allowed us to calculate a future value of the account. We want to take a look at an example that switches it around and asks instead for what was the principal, what was the initial investment. So in this scenario, Julio invests a sum of money in a savings account with a fixed annual interest rate of 5.15%. So I'm going to start underlining some data. So that's my rate. I know I'll need to convert it. So that's 0.0515. I also see here that the investment is compounded semi-annually. So we need to get used to some of these words. Semi-annually means that it's interest compounded twice in the year. The prefix semi means half. So my n value from that word is going to be 2. We should list out some other words just so that you're aware of what the possibilities are. So if we start with annually, the n value would be 1. Semi-annually is every 6 months we would calculate the interest, so n value equals 2. We also have quarterly, which we saw in our first example. Quarterly means that interest is compounded every 3 months. So there would be 4 compoundings in a year. Monthly, since there are 12 months in the year, the n value would be 12. Weekly, there are 52 weeks in the year. Daily, n value would be 365. And really daily probably would be for compound interest, probably the most frequent. There's one more version that we'll see called continuous compound interest, but we'll save that for now. That involves a different formula. But ours is semi-annually, so our n value is 2. So we are looking for after 6 years, so that's going to be our time. The balance reaches $9,939.52. So that's my future amount. We'll call that A of T, which is A of 6. Our question is, what is the amount of the initial investment? We want to find what's the principal. So let me bring the formula again. We'll substitute values in for the variables we know, and that'll give us an occasion to solve for the principal. So again, here's our formula. Future amount equals principal times 1 plus r divided by n to the power of nt. So I'm going to plug in what I know. A of t we saw was $9,939.52. So notice we're able to plug that in on the far left side. Principal, I don't know. The rate we had converted over to the decimal 0.0515 divided by n value of 2 to the power of 2 times 6 years. And so the thing that we're trying to solve for once we got this set up is the principal. Now we'll input this in the calculator, but I want to get it to a place where I can input it all at once. So to solve for P in this equation, I'm going to divide by this whole base to the power of 2 times 6. And here on the right-hand side, that's going to cancel the expression. So what it'll do is it'll leave P by itself, and the expression that we got to evaluate to find the value of the principal is this one, 9939.52 divided by 1 plus 0.0515 over 2 to the power of 2 times 6. So you do need to do a little bit of preliminary solution. Excuse me. But at that point, you can solve using the calculator as well. So let's take this to Desmos and plug it in, get a value. And we'll type it in according to how we solved it in that last step. So again, the future value 9939.52 divided by base 1 plus 0.0515 over 2 to the power of 2 times 6. And what that gives us is the approximate value of $7,326. And if I were to round, it would be 0 cents. So we'll take that back to our notes screen to finalize that second example. And what we'd say here is that the principal has the approximate value of $7,326.00. And just to see, is that a reasonable amount to be starting with? And it seems good because the future amount is bigger. We're always looking for some kind of growth in compounded interest investment. So that seems very reasonable. Thank you for joining for this investigation of calculating future amount and also initial amount in compounded investment. Thanks for joining. See you soon.